Well, hello everybody, Dave here, and this is a lesson on simple harmonic motion. We'll discuss what they are, different examples of them, and we'll talk about them in terms of kinematics, dynamics, and energy. So to begin our discussion, let's remind ourselves about springs. You'll recall that a spring has a natural length that it doesn't want to change. If we apply a force to it and we stretch it or compress it, it naturally will snap back into position if we let it go. Well, we call this force the elastic force, and we know that because it always wants to restore its equilibrium position, that it's considered a restoring force. Now, Hooke's law told us that the elastic force is equal to k times x, where k is the spring constant, and x is this displacement from equilibrium position. You'll notice that there's a negative sign on Hooke's law. Now in physics, you'll remember that negative signs aren't necessarily used in the same way that they're used in mathematics, that they are more so to denote direction, and whether it be a direction of motion or a direction of transfer. Well, this negative sign is meant to represent the fact that it always wants to counteract the manipulation you do to the spring. So although it's listed on the equation, when you use it mathematically, you typically don't include it. I really strongly promote the idea of understanding direction in terms of the physical situation instead of relying on negative signs to hopefully get you the right direction in the end. So let's take a mass and hook it up to a spring in a system like you see to the diagram on the right. I'm going to stretch the spring out so that the mass is clearly to the right of the equilibrium point, and then I'm going to let the mass go. Well, the spring is naturally going to want to go back to its equilibrium position, so it's going to start to move to the left. But what's going to happen is this mass is going to gain inertia, and by the time it gets to the equilibrium point, this inertia is actually going to drive the mass through the equilibrium point, and we're going to start to compress the spring. Well, if we're compressing the spring, now we have an elastic force counteracting this compression, so again there's going to be a force pointing back towards the equilibrium point. At some point, this force is going to overcome the inertia of the mass, and it's going to start to push it back towards the equilibrium point. Well, if there is no friction present, this motion is going to continue. Well, we give this a term, we call it an oscillation or a periodic motion. And in the case of the force, so long as the net force is along the direction of motion and it obeys Hooke's law, we are going to refer to this as a simple harmonic oscillator, and this is a simple harmonic motion. So to begin our discussion of simple harmonic motion, we're going to go back and take a look at the horizontal system again. But this time we're also going to include a vertical system where we have a mass that is centered right over top of our horizontal system's block. We know that we applied a force to stretch the spring out, and as we stretch the spring out, there is an elastic force pointing back towards the equilibrium point. And what we've done is we've stretched it to some set distance, which we'll call x. Well, at this point, the block is stationary, which means that this is actually the farthest distance away from the equilibrium point it will be. As the system oscillates, there won't be additional force added to the system, which means it can never get past this point. So we give this point a specific title. We call it the amplitude of the oscillator. And you'll see in the vertical circle above, the amplitude is actually representative of the radius of this circle. At this point, I also want to mention that there are other oscillators that we could represent in a similar way. If you take a look at a springboard like what you'd see at a pool, if we take that and we put a mass on the end of it and bend it down, if we let that go, what would happen is it would oscillate up and down vertically. Well, that vertical displacement from its natural equilibrium point of straight to this bent down part would be the amplitude that we would talk about. The bottom diagram is a pendulum. And with a pendulum, we would take it from its natural equilibrium point of hanging straight down and pull it back to a certain point so that when we let it go, it will oscillate back and forth. It is that horizontal distance away from the equilibrium point that would be, in this case, the amplitude of our oscillator. So if we now remove the force from the block is naturally going to move towards the equilibrium point because the only force present in the system now will be the elastic force pointing towards the equilibrium point. At the same time, you'll notice that we've done a rotation of the mass in the vertical circle to follow the center of mass of this horizontal block. And what you'll see is at this point here, we've labeled a couple of different quantities that are worth mentioning. We notice that the horizontal distance that the block is away from the equilibrium point is the same as the horizontal component of this right triangle that we've formed on the vertical circle. You'll also notice that the mass has subtended an angle of delta theta at a velocity of omega. So you'll remember that when we deal with circular motion, that we typically talk about it in terms of angles, and we talk about it in terms of angular velocities, angular accelerations, and things like that. One of the important quantities to recognize is because we've labeled the distance away from the equilibrium point as the amplitude, that the hypotenuse of this right triangle is also representative of that particular quantity. So we can begin to formalize some of these quantities by reminding ourselves that omega, the angular velocity, is equal to the change in angle over the change in time. Well, if we do one full cycle, that would be a total angle of 2 pi radians. And the time that it takes to do this cycle, we're going to define as the period, capital T. At the same time, we might want to understand how many cycles happen per unit time, typically per second, but sometimes it could be more. Well, when we want to find this quantity, we're actually trying to find the frequency of the rotation itself. You've heard of frequency before because the units of them are cycles per second, which are more commonly known as hertz. So if we relate these quantities to our physical distances that we were talking about before, we can actually use some simple trigonometry to find the horizontal displacement of this block in terms of the angle and the amplitude. And so you'll see that we've labeled x to be a cos delta theta, but now instead of referring to it as delta theta, we're actually going to substitute in the angular velocity times the time of travel. And what we end up with is an equation that represents the position of the oscillator with respect to time. It's more commonly seen with a substitution of 2 pi f for omega. So the first equation in bold there is x is equal to a cos 2 pi f t, where f is the frequency of the oscillation and t is the time that the oscillations have been happening for. A is, of course, the amplitude. Now you'll notice that I've also listed an equation for velocity and acceleration. And to derive these equations, we would actually have to do a bit of calculus, because if you've been through calculus, then you understand that the first derivative of the position equation will give us the velocity equation, and the first derivative of the velocity equation will give us the acceleration equation. So these are all related according to derivatives, but the important thing to recognize here is that they're all related to trig functions, and they're all related in terms of omega, frequency, time, and amplitude. So these three equations are the essential kinematic equations in describing the oscillation motion of a simple harmonic oscillator. We also want to bring in our discussion of energy, and for that we have to remind ourselves from previous lessons that the elastic potential energy is equal to 1/2 kx squared, where again k is the spring constant and x is the displacement from the equilibrium position. Now if we use the conservation of energy, we know that all the initial energy has to equal all the final energy. And we know that all the initial energy is going to be that elastic potential that was the result of our stretching out from equilibrium to our distance x. And as it moves, there's now going to be a sum of two different energies. There's going to be the kinetic energy, because of course it's gaining speed and losing speed, and there's still going to be some elastic potential left over. If we take this equation and solve it for v, what we now have is an equation that represents the velocity of the oscillator at any point in its motion with respect to the spring constant, the mass of the object moving, the amplitude, and the distance away from the equilibrium point. The plus or minus, of course, represents the fact that it's going to pass the equilibrium point, at which case we are now going to refer to it as moving backwards and backwards again. Now there are some great implications associated with this velocity equation that are worth mentioning. If we get to the equilibrium point, the x squared term would disappear, and what we now have is a maximum velocity that can occur. At the same time, if we substitute in the amplitude for x, what we would end up with is the velocity being 0. So what this is doing is this is giving us some max-min scenarios. So we know that the maximum velocity of the oscillator is going to occur as it passes by the equilibrium point, and it will be 0 velocity at the endpoints when it's reached the amplitude distance away from the equilibrium point again. We can also explore this discussion if we focus on the vertical circle alone. If we think about it in terms of circular motion, we'll remember that one of the big assumptions that we make about circular motion is the magnitude of the tangential velocity will remain constant throughout this motion. Well, if we determine the distance that it travels in one rotation, we know that that's the circumference of the circle. So in our case, it's 2 pi times a. And the time that it takes to perform this rotation is the period of oscillation, in this case t. We can rearrange that equation for t in terms of the amplitude and velocity, and that equation alone could help us out, but we can even take it one step further, and we can actually use the conservation of energy in that we create an equation for A over V naught based upon the quantities of the oscillator itself, specifically the mass of the object and the spring constant. Well, if we substitute this into our equation for period, what we have now is an equation for t in terms of the properties of the oscillator itself. So t is equal to 2 pi times the square root of m over k, where m is the mass of the object oscillating and k is the spring constant of the oscillator itself. So let's track the center of mass with respect to the angle subtended by the vertical circle and see if it creates a shape that maybe we can recognize. We can see that as we go, we start from a maximum point, which we know is the amplitude, and then it dives down to a point where we are now at the equilibrium point, and then it goes the other way until it reaches a point that is the magnitude of the amplitude away again, and then it goes back and it repeats. Again, this is the signature of a periodic motion or an oscillation. Well, you'll remember that we derived an equation for position with respect to time, and it was represented as a cosine function. Well, for those of you that have been through a math class where we've actually graphed a sine function and a cosine function, you'll recognize that this graph right here is actually a cosine function. So it is representing exactly what we expected from our algebraic derivations originally. So let's remind ourselves about the different properties of a wave. We have here a cosine function, and I've labeled some important quantities that we discuss a lot in physics. You can see that I have made a mark of the point at which the wave starts to go down, and then it goes up, and then it goes back down, and then just before it repeats itself, I have cut that off. Well, we refer to this as the wavelength, and the way I like to think about wavelength is the distance at which it takes this wave to repeat itself. You can see that we've also labeled the amplitude for both the bottom part of the wave and the top part of the wave. The magnitude of the amplitude will be constant regardless of if it's top or bottom. What will be different is whether it is to the left or the right or above or below the equilibrium point, which in this case is the horizontal axis. When we get to the point above or to the right, we refer to that as the crest. And when we get to the lowest point to the left or below, we call that the trough. So I've given you these definitions again. We talked about them in the previous slides, but please keep note that when we discuss periodic motion and oscillations, these are the quantities that you are likely going to need to discuss at some point. If we change the oscillator to be vertical, now the weight of the block is going to have to be considered in the system. So we have here a diagram on the left, and you can see that the farthest left spring is the one at its original equilibrium length with nothing attached to it. When I hook up a mass to that spring, what's going to happen is it's going to stretch until it reaches a new equilibrium point, in which case is going to be x1. Well, at this point, the spring force pointing up has to be equivalent to the gravitational force pointing down because there is no motion up or down. If we take these two forces and equate them to each other, we can substitute in Hooke's law, and we know the calculation of the weight of the block. We can actually come up with the distance that the spring has stretched from its original equilibrium point to be mg over k, where k is the spring constant. So let's take this system and grab the mass and stretch it down an additional distance of x2 and let it go. Well, what will happen now is that it will oscillate around this new equilibrium point at an amplitude of this distance x2. If we consider the energy discussion for this, I want to let the zero potential line be this stretched out distance of x1 plus x2, and when I let it go, now we're going to have three different types of energies to consider, because we have the kinetic energy of the mass in motion, we have the spring elastic potential energy that still exists in the spring even though it's starting to compress, and we now also have this gravitational potential energy associated with the mass's distance above the zero potential line. Now let's take this equation and play with it a little more. I'm going to take this squared binomial and I'm actually going to expand it out. And when I do so, I'm going to end up with two terms on the left and right side of the equation that will cancel out. And in this case, it's the 1/2 kx1 squared. Now I've highlighted the kx1 because we will recall that when we left the system stationary, we actually derived an equation where x1 was equal to mg over k. Well, if we take that now and we reorganize it so that it is k times x1, we can now substitute in mg for kx1, and what we have are two more terms on the left and right side of the equation that will also cancel out. And what we end up with is 1/2 kx2 squared is equal to 1/2 mv squared. Well, all that has shown us is that the gravitational potential energy in an oscillating system is not to be considered when we are discussing the energy of the system itself. And that's an important thing to recognize, because it shows that the energy situation in both a horizontal and vertical system can be dealt with in exactly the same way. One of the classic questions that's asked about oscillators is its maximum and minimum quantities at various positions along its oscillation. So in this case, we've tracked the point where it is an amplitude above the equilibrium point, an amplitude below the equilibrium point, and the equilibrium point itself. And we can see that when it is fully compressed at its maximum above the equilibrium point, the position is a maximum above the equilibrium point, which means that the elastic potential is also at its maximum. The velocity at that point has to be zero because there's no kinetic energy at that point. If we talk about it in terms of forces and instantaneous acceleration, we can see that at this position, we now have a spring force that's pointing straight down along with the gravitational force, which means that the sum of the forces at this point are a maximum. Well, according to Newton's second law, if our net force is maximum at this point, then the instantaneous acceleration at this point will also be a maximum. When we get to the equilibrium point, however, we are now zero distance above the equilibrium point, which means we have no elastic potential energy. But at this point now, if there's no elastic potential, all of the original potential has been converted into kinetic energy, so both the kinetic energy and the velocity are a maximum. When we talk about the sum of the forces, we are at the equilibrium point, which is where the spring force pointing up was equivalent to the gravitational force pointing down, so both the sum of the forces and the instantaneous acceleration at that point will both be zero. When we get to the bottom end of this oscillation, the exact same discussion that we had at the top end is now going to be true. We are the maximum distance away again, which means we have the most elastic potential energy. There is no kinetic energy to speak of. When discussing the sum of the forces and the instantaneous acceleration, we now have a spring force that is much larger than the weight of the block pointing down, which means at this maximum displacement away from the equilibrium point, we're going to have a maximum sum of the force again, which means that its instantaneous acceleration at that point will also be a maximum. So definitely understand this chart and how we came up with these conclusions, because conceptually these are great questions to ask in future assessments. Another classic simple harmonic oscillator that's discussed is the pendulum. However, if you take a look at the diagram here, we can see that the restoring force is going to be the tangential component of the weight of the mass and not some sort of spring force. Well, by definition, we required that the net force had to obey Hooke's law in order for it to be a simple harmonic oscillator, and this component is equal to mg sine theta, which does not look like Hooke's law at all. However, if we limit how far we pull the mass of the pendulum back, we can use the small angle approximation that the sine of this angle is approximately equal to the angle itself. We limit this to about 15 degrees or pi over 12 radians. It's important to recognize that when we're dealing with harmonic motion or any of the sine functions in this particular lesson, we're always in units of radians and not degrees. Well, when we do this, we can substitute in theta for sine theta and get the tangential force is equal to mg times theta. From some math class, you would have learned how to calculate the arc length, and the arc length, which is the displacement distance away from the equilibrium point, is equal to, in this case, L, which is the length of the pendulum, times theta, which is the angle that we've moved it from the point. And what we do is we rearrange this for theta to be S over L, and we substitute that into our tangential force, and we get this equation of mg over L times S, where S is the displacement distance away from our equilibrium point. Well, we've already determined that K was equal to mg over L in a previous example. And if we substitute this into our tangential force, we get the equation of Ft is equal to Ks, where S is the displacement distance away from the equilibrium point and K is the spring constant. So wouldn't you know it, now we have a restoring force that looks exactly like Hooke's law. So based on this proof, we can now take our equation for period and substitute in our spring constant, which is representative of this oscillating motion, and we can get a new equation for period in terms of the properties of a pendulum, which in this case is the length of the pendulum and the acceleration due to gravity on the mass itself. You'll notice a couple of things. First and foremost, it is independent of the angle that we pull it back. Remember, this is only true in the case of a small angle approximation. We've limited it to about 15 degrees, and if you go farther than that, 20, 30, 40 degrees, the accuracy of this equation for the period will certainly drop. You may also be interested in how it's proportional to the length of the pendulum. If you look at other aspects of physics that we've already studied, if we talked about this in terms of a rotating massive object, then we could talk about it in terms of the moment of inertia and the torque. And what's interesting is as we increase this length, we are certainly increasing the torque, but we are way, way, way increasing the moment of inertia, which means that that quantity itself is far more important in the overall motion of this pendulum. And so the fact that it is dependent upon the length of the pendulum is no surprise here. So in discussing pendulums in an energy case, we have to recognize the fact that the length of the pendulum actually isn't going to change. It's a rigid quantity, which means that the classic sense of an elastic potential energy won't exist in this case. There is nothing to compress or stretch. However, we are changing the height of the bob from point A to point B, which means that there is certainly gravitational potential energy to consider here. If we replace the string with something like a spring, now we would have a much different question that would involve that motion as well as the motion of the swinging pendulum itself. The tricky part about a question like this then would be to find the height that the bob drops from point A to point B. A lot of people mistakenly use the length of the pendulum as their only length. However, what we see here is that we've actually created a right triangle. And of this right triangle, if we find this component of the right triangle, because we're going to have the angle that was subtended to get point A to point A, then we actually have a equation that the total length of the pendulum is this component plus the little height h. Well, what that means is we can find this little height h simply by subtracting this vertical component from the total length L. Now, to calculate the velocity of the bob at point B, we're going to let the horizontal line through point B be the zero potential energy, and we're going to equate then the initial potential energy at point A to the kinetic energy at point B. Rearranging it, we get this equation of V is equal to the square root of 2gh. Hopefully this reminds you of an equation that you derived many times in your studies of circular motion. There are also other quantities that you may be given in a question that are meant to confuse you. However, if you're given the angle relative to the horizontal surface that the pendulum is attached to, you can either use an alternate interior angle argument to put it down as an angle around point A, or you could simply do the complementary angle of 90 minus this angle to get our originally labeled angle of theta. If we're asked to find the amplitude of a pendulum, well, that's simply the horizontal distance from the equilibrium point. And so if you're asked for the amplitude, don't simply use the length of the pendulum like we did with a previous discussion of a vertical circle. In this case, it's going to be this bob moving back and forth horizontally at this distance of x. If we create a chart like we did with a vertical harmonic oscillator, you can see that at point A, we have a maximum horizontal distance away from the equilibrium point. We also have a maximum height above our zero potential. And if we have our maximum potential energy, that means that we have no kinetic energy to speak of, and all of the forces at that point are a maximum, which means, like with the vertical case, we will have a maximum instantaneous acceleration there. If we talk about it at point B, well, now we are no distance away from the equilibrium point. We are no height above our zero potential line, which means we have no gravitational potential to speak of. That means all of it has been converted into kinetic energy, which means our velocity at this point is a maximum. The sum of the forces here, because it's at the equilibrium point, are going to be equivalent to 0. At C, it's the exact same argument that we had in point A, that we're at a maximum for potential and height, we're a maximum for amplitude, and we're a maximum for the sum of the forces in the instantaneous acceleration. You'll see the diagram on the right here. What we're showing is a graph of potential as a function of displacement from the equilibrium point, kinetic as a function of displacement from the equilibrium point, and the total energy as a function of displacement from the equilibrium point. These are important graphs because, again, they represent a conceptual understanding, and you'll notice that as potential goes down, kinetic goes up. This is conservation at its best, and the total energy is a horizontal line, which means it is constant throughout. Energy is conserved. So everybody, that's simple harmonic motion. That's horizontal, vertical, and a pendulum. It's important to recognize that these derivations are not necessarily going to be required of you in whatever studies you're doing, but at the same time, I always like to know where these equations come from, and most importantly, what assumptions have we made to get those equations. Best of luck to you with your practice problems, and we'll see you again.